Okay, on to the next page. So we're starting off with the digital logic problem, and we've got sort of a problem statement here, and we're trying to filter phone calls based on these two conditions. And we've got a couple variables here, whether the phone rings before or after a time, if the caller's in the contacts list or not, and if it's a repeated call or not, and then if the call is screened or not. So we got to fill in this table to implement the desired logic. And that means that we're going to just start by sort of alternating zeros and ones after every 4, and then alternating after every 2, and then alternating after every 1, just to get all of the possible combinations of zeros and ones that we can have. Really, we're also just counting up in binary 0, 1, 2, 3, 4, 5, 6, right? 7. And so now we need to figure out what V is, and that's sort of our final condition. So we've got call is screened if it's a 1, or call is not screened if it's a 0. And up here, we decide that we're going to screen calls, so V equals 1 when these two conditions, or one of these two conditions, are true. So let's just kind of annotate this with the variable values. So rings before 2200 is T equals 1. Caller not in the contact list is C equals 0. So that's our first case up there. And then if the phone rings after 2200, that's T equals 0. Caller not in the contacts list, that's C equals 0. And not a repeated call, that is R equals 0. So that's just going to help us figure out when V is equal to 1 here. So our first case, T is 0, C is 0, R is 0. That's the exact case that we have listed here, and it's and. So that means that V is 1 because it's after 2200, caller is not in the contacts list, not a repeated call. Here we've got after 2200, caller is not in the contacts list is a repeated call, so we're not going to filter that. So someone's been really trying to reach us. After 2200, caller is in the contacts list, we're not going to filter that. And same thing here, it doesn't matter that it's a repeated call. So that's our first set. Now we're before 2200. And so before 2200, caller not in the contacts list. Well, that's this top condition, so that's going to be a V equals 1. And you note here that we don't have the and this is not a repeated call, so it doesn't matter what that changes to. This is also just going to be filtered. And then for these, this is in the contacts list, so not filtered, and is in the context list, so not filtered. So that's our truth table. That's all we need to do is basically just follow the logic in English and translate that to binary variables. So then our second part is write out a Boolean expression for V based on your truth table. And what we want to do here is find all the rows where we have a 1 in the table for the final output, and that's going to be V equals this. And then we're just going to note what the values of the variables need to be to make V equal to 1. So if we have T equals 0, C equals 0, R equals 0, then we need T naught, C naught, and R naught to be true, right? So that line over the top is knotting them. So really it's just if you see a 0 in the column leading up to a 1, you're knotting it. If you don't see a 0, if you see a 1, we're going to leave it the same. We're going to add these together because this ORs it. So this is basically going to be not T, not C, not R. Or the next row we have is T, C naught, R naught. Or T, C naught, R. Okay? We can simplify this in a number of different ways, and all of those are also acceptable. So if you have a simplified version of this, you're welcome to give that as a solution as well. So moving on to part number 4 here, since it's on the same page and it's heavily related, right? This is fill in the truth table for the transistor circuit shown here in terms of logic 0 or 1. So we look at the circuit and recall that when we have a 0 coming into that transistor, we are going to not include that transistor. We're basically going to leave that as a gap. So for our first row here, we'll basically just have our grounds here at the bottom. And we're going to have a disconnect between each of those and the top of the circuit, because we're assuming that this is 0 coming into each of them. So this is 0, 0, 0 is what we're showing. And then we've got our output going to be out, and we've got our resistor going to our 5-volt input. And we can see that because nothing's connected here, our output is going to be the 5 volts that are coming into this circuit. So 5 volts is considered A1 in the output. When we move on to the next row of the table, we're going to connect C through. And since we have a 1 there, that means that transistor is active, and we just basically draw a line where that transistor would be. So now that we're connected to a ground, that's where the current's going to flow, and so our output, which is weaker generally, is going to be a 0. And we're going to have the same exact scenario for the rest of these, right? As soon as we connect one or more grounds to this circuit, we're going to have a V out of 0. And so we're just going to be able to fill in the rest of these with a 0 here. In many cases, you might have to do a little more complicated analysis, but again, the basic concept is if that transistor, the input to it is 0, we just remove it and assume that there's no connection there. If it is 1, we assume that that wire is there and that it's connecting it to whatever's on the other end. So that's it for that page.